Alrighty, hello there. Welcome to the live stream. Today we have the laptop back, and that pleases me. So what I'm going to do is, as is my wont, I'm setting up all of my stuff. I'm going to pause my little YouTube thingy while it's looking at the screen so I don't see things bouncing around all over the place, and let's set up things like chat. If you're in chat, you'll be on screen momentarily. Bear with me for a second. I've been doing a lot of experimenting and new things. For instance, check it out. I have got camera views on things. Like that is a synthesizer view, but if I'm standing and recording a bass part or a guitar part on this camera view, you would be able to actually see the instrument and how I'm playing it. If I stand in just the right place, then what I'm doing with both my hands is visible. So that's kind of neat. And I got a nice wide angle view, which currently is showing the back of this laptop that I'll be coding on. But today we're doing asymmetrical distortions. And let's jump right on over and start doing it. Now, when I say asymmetric, it is not exactly like single-ended triode. See, the deal is, what I want to do is set up something that acts like the kinds of distortions I've been using in all of these emulation plugins. McAdee, beyond McAdee to the Z-series plugins, which are using the same basic concept. And these are all the basic concept of, hang on a sec, moving around Windows a little bit more. If I put this here and scooch that there, then I can see the monitoring of OBS without the little face talking away. I got it. It's a crazy thing, but I find it almost overwhelming that if you're making videos and live on video and the camera's over there and on screen right in front of you within earshot is what's coming to mind, but within your field of vision is your own face talking away like mad and doing stuff. You're staring at your face constantly if you can see it. So I think that's terrible, so I always go to some trouble to try to defeat it. Anyways, here's what we're going to do today is a plugin that I'm calling Bendybus, simply because my idea behind this is, firstly, I want to do a plugin that can give you the power to sort of dial in any degree of McAdee style clipping. And that's a kind that I've set up where it's all based on taking the sample that you're at. Say it goes from 0 to 1 and to -1. And you're doing a kind of clipping, which you can do by going, the sample is equal to itself minus some other factor. And as it continues to get larger, the like if you have, let's just load something up. You can see this screen, right? I have this on screen, yes? Yes, I do. I'm going to be a little bit scattered because I've had some interesting experiences over the last week or so, and not all of them have to do with the replacement switcher, which is letting you see all of this. So, mental rebooting that may be leading to lots of wonderful new plugins and inspiration going forwards. For now, let's open a recent file or a relevant file. And my notion of a relevant file would be simple audio unit. And we're going to go and look at directly McAdee. Not because there's anything here that I need to copy to make this work, but because it's a really good example of what I'm talking about. Now, what I have in mind is not going to involve all the filtering and things that this does, but the heart of McAdee, in terms of clipping, is this part. And how this works is we are hard clipping the maximum range to +1 or -1. Then we're doing input sample minus a factor here. Let's step that out, and then scaling it back. Meaning that's as much diminishment as you can get. Past that, it's just hard clipping. And this, of course, is equal to one, two, three, four, five. This. So we've got basically this, and that's how McAdee works. Now, what does that do? Well, one of the things about this is if we had input sample minus input sample, just all by itself, if it's positive, like between 0 and 1, it's going to get smaller as it gets applied. If it is negative, then we're subtracting a negative number. That's the same as adding a positive number. That's also moving it away from the side of the voltage swing that we're on. So if you do input sample minus input sample by itself, then you're always reducing the range of where that value can go. If you do input sample times input sample, one of the things about multiplication is if you multiply something by a negative number, you flip the bit of it. And for that reason, two things happen if we're doing this. And this is all very basic, but I'm talking through it just in case anybody watches the coding thing. This is the kind of stuff you got to do if you're programming DSP things and thinking them up from scratch. A little chai tea there. Input sample minus input sample times input sample means that if it is positive, like positive 0.5, well, 0.5 times 0.5 is 0.25. So input sample minus that, it's going to go down to, it's not going to scale back all the way. We now have a subtract there that's using a number that stays smaller until it gets all the way up to 1, at which point 1 times 1 equals 1, no change. Thing is, if you are at 0 or less than 0, input sample is negative 0.5, shall I say. that has just flipped the bit of your subtracted value. You're still doing input sample minus input sample. Unfortunately, or fortunately, because this is what we're going to be building up to, if you're doing input sample minus input sample times input sample and it is negative 0.5, that becomes positive 0.25 because it's a negative number, and then you multiply by another negative number and you get the result, but multiplying by the negative number flips the bit. So that means that both in positive swings and in negative swings, when you get that close to when you take the number that you're using, if you have the even number of multiplications and you have the bit being flipped so that it's automatically positive no matter what you do, that's taking the waveform on the positive side of the waveform and it's going to clip it. It's going to become smaller. But since what you're doing is moving it in the same direction, if you're on the negative side of the waveform, that becomes an expansion. That means that you've got your negative number, you're coming up with the amount of variation that it changes, but instead of everything contracting, clipping towards the center, getting more distorted, getting quieter, one side gets quieter, one side gets expanded, gets louder. And that is why we're talking about asymmetrical distortions. I can probably also do a little demo of this pretty quickly and easily. I'm just talking over this using McAtee because that's kind of where I started with. So we'll repeat. Using one version of the variable and subtracting that means that no matter what side of 0 you're on, it's going to get smaller, closer to 0. 2 means that if you're positive, it is going to get closer to 0. If it's negative, it's going to get farther away. It's asymmetrical. 3 times, oh hey, we've just included the sign bit again, so it's going to get closer to 0. But now, stuff near the center of the waveform is continuing to get reduced more and more. Every time we're multiplying things by the size of what this variable started out as, that means the more of these we put in, the more linear it is towards the center of the waveform. If you have very small numbers in here and you're doing this with them, what's going to happen is if you have many instances of this, like a power of 5 or a power of 7 or so on, it's going to act a lot more like just plain hard clipping. The center of the waveform is going to be just about untouched. And then only when you start to get really close to the edge of clipping does it spike up to become a significant amount. Also remember, I'm doing this part of the clipping and making sure that it doesn't go beyond 1, because of course, say if you had the input sample go all the way up to, say, 2. And then we're doing this thing that's supposed to clip it, in that we're supposed to have it go no effect when the numbers are small, and then the closer it gets to 1, it doesn't matter how many times you multiply it by itself, it's still going to be a large-sized number. And then we scale that to determine where our clipping threshold is going to be. Well, if input sample is larger than 1, guess what? The amount that we're subtracting by just became much bigger. 2 times 2 times 2 times 2 times 2 means it is 2. It's already beyond normal clipping in the DAW. And then rather than dialing it back and making it become closer to 0, it's going straight through 0 to the other side with an enormous, massive voltage spike. And I'll demonstrate these things as well. But that's also a reason why we're using this to cut down the maximum amount that we cut things back by, So what might be interesting to do is we'll fool around with some of the possible outcomes when we don't do those things. The bottom line behind what I'm going to be doing, though, is we have two separate algorithms sitting here in this capacity as how this works. Odd-numbered ones will clip, make stuff get smaller, because this subtracting is always going to move things towards zero, or through and beyond zero. But even-numbered power factors, like input sample times input sample, or input sample times input sample 4 times, becomes asymmetrical with exactly the same linearizing effect at the center of the waveform. Like whether you're doing it symmetrical or asymmetrical, it's going to produce increasing linearity towards the middle of the waveform if you have large numbers of power factors in here, if you're multiplying it by itself many times. And then remember, this is 5 times, so this is one where it's going to clip. What do we do if we want to make it be asymmetrical but also 5? We do the same thing that we do if we want it to be symmetrical but with an even number. Like if we're trying to do input sample times input sample, that's a very, very soft clip, but it is also a asymmetrical calculation. But then if we do input sample times absolute value, I think it's fabs that we use here, that's going to switch the type of calculation again. So what we've got is a set of calculations that can be done using any number of discrete power factors. In fact, if I use the power calculation, I have been told that using POW for this is terrible. Well, here's another possible reason that you might want to use it. If you use POW, one of the things that happens is you're calculating the actual result in higher resolution than you would using just like a floating point number and doing input sample times input sample times input sample and so on. Yeah, because POW runs more accuracy for the purpose of being able to do this calculation without, think of it this way, right? Let's bounce back to this. Think of it this way. We're doing this thing where we're going like input sample times input sample times input sample and so on. Let's say we have a really low resolution number. And let's say we have an integer. We could have an integer. And the integer is like 3 times 3 times 3 times 3 times 3. Unfortunately, when you do 3 times 3, you've now got a result of 9. If you do 4 times 4, you've got a result of 16. And you're continuing to multiply, and the amount of error that's being produced every time think of it a little bit like floating point calculations. In fact, floating point calculations are relevant to this. As you continue to multiply using just plain the multiply operator, which is faster, what's going to happen is the amount of inaccuracy in the calculation is magnified by the number of the power factor that you're using. And as such, you do your initial input sample times input sample, and then throw a whole bunch of other ones on there. And then the amount of error that you had from that original input sample times input sample is getting magnified by basically the amount that you're multiplying everything by. It may or may not be relevant to use in situations where the numbers are not larger than 1. I think the numbers being smaller than 1 might produce a situation where you're fairly safe at just continuing to do the multiplying, because the inaccuracy that you generate will just keep getting scaled back. Like, in terms of the limitations of what you're doing, having the multiplications be smaller than 1, having the power factors get littler rather than bigger, means you're losing accuracy and ability to handle the numbers that are extremely large. But we already know that we're not doing extremely large numbers, so it's a moot point. So that's an interesting thing to arrive at. If that is the case, then we don't lose anything in this particular context by doing just the straight up multiplications. So we don't need to use the full-on power factor for specifically this, or honestly for anything, because the other things we use them for are calculations of control parameters, and those tend to be between 0 and 1 as well. Bottom line, if we're doing power factors in giant big numbers, then not using the pow parenthesis operator, the giant big numbers will hang on to accuracy with a sort of fine granularity, and generating tiny numbers by having stuff that's less than 1 and multiplying that by itself a cajillion times. Using the power factor means that hangs on to the ability to represent numbers at large granularity that we know we're not doing. So that's all very interesting. It's a little babbly, though. I'm going to have to move on to doing the actual coding of this. Now tell me, thank you, don't save. There we go. That was just for demonstration purposes rather than wanting to change McAdee. Let's quickly get something. That we can work with. And here's one possibility. We got a lot of stuff going on here. Alrighty. So what we have now is a plugin that we should probably be able to build. It may or may not. No, it's not going to build instantly, but the second time around it will. This particular code tries to build sort of from top down, meaning that it tries to make the source, and then it builds public utility, and then it builds AU public, which it needed to have for this other stuff. Oh, and I had better, it complained about question mark, question mark, question mark, question mark, which is here. I'm calling this plugin Bendybus because we're doing distortions on opposite sides of 0, and they get to do entirely separate things. So it's a Bendybus. It can do whatever. It doesn't have to follow the same rule. So we've got that. The reason we had all those errors was because it was trying to build AU source before it built public utility and AU public. Now that it's built those, it'll be fine. except for that we have an unused variable here. That's fine. We'll make that go away and now what I've done is I just made a McAtee distortion stage. Let's do alien kittens. We've been hearing alien kittens before, which starts at 1.0. Actually, let's start it at 0. And increasingly distorts as we bring this in. But we'll notice something interesting here, which is that our waveform, maybe a good thing to look at would be our sine waves. Let's fire up a sine wave. Let's fire up a base sine wave so it's real easy to look at. That ought to work. So what we're going to do is normalize all of this to 0 dB. And this is going to show us what our function does. It's not going beyond 1, so we're not going to have any problems with the clipping. And when we do this, what we'll see is we can start having more intense distortion, and then something else happens. And when I actually apply it, you'll see it on the waveform. Here's what we're getting. Here's our initial base frequency. And what we're doing with our wavefolding is, this is the point where it zeroes out, and the amount of energy being subtracted is equal to the amount of energy that's there. As we continue going and the sine wave goes all the way over to 1, we're getting a subtraction of 1. So it rounds softly over and becomes, which is interesting, maybe we should make a plugin that specifically does this, right? We'll call it Bendybus. Maybe this might be something to do. Who's to say we can't drop a plugin idea and immediately start doing another one? Oh no. Oh, hang on. Oh, I'm sorry. I switched over to that. Yep. Thank you. Nobody mentioned it. I forgot to do that. That's one good thing about being able to see your screen when you go, is that you can tell when you've not switched over yet. We'll undo. So here's what we've got. Girk mentioned this a while back. I'm going to leave it on this for the time being. I'm not going to switch back forward over to the camera. I have no idea. POP 1976. So this is what we built. We built this, and we've got this control where the other one, where McAtee does this, and then does the power factor of 5 times gain. And I wonder what we're going to get with different factors here too, but on McAtee, this is like 0. 176 something or other. I did in fact respond to somebody's comment on the Blackmagic Design subreddit because somebody was complaining about how their webcam output would cut out. The webcam output cutting out seems to be the first sign of trouble in the A10 Mini melting itself. So I made a long post about that, which seems to have gone over fairly well. I've also been experimenting with other things, like this microphone that I'm on. I've done a little testing and plugged it into the microphone input on the A10 Mini to see whether the A10 Mini does in fact generate phantom power that can power a little microphone like this. Turns out it does. Turns out you can plug these little lavalier microphones into the A10 Mini, turn on the mic, set it to mic, and the phantom power that people thought was contributing to the overheating problem, and I don't think that's true, is capable of running this little mic. And what that means is if I get back into doing like music jamming using this kind of stuff, like my cameras and so on, all of that, I'll be able to plug the lavalier mic into the ATEM, and then it's not coming through the speakers. And I can do whatever I want, not worry about running it into Logic and recording it when I don't want to. In fact, it'll free up a microphone space. I'll have a separate spot for a proper studio microphone, and then also the lavalier plugged into the ATEM that only goes to the stream and doesn't go to the speakers. So all of this is very handy. Get back to this. What we've got here is a thing where we're doing the MACD calculation, and that clips. And if we set it to about I think that's about where MACD actually was, we can hear what it's doing as well. And you can hear it's distorting a little bit now, and then it's clearly distorting more. And then if we apply that, that's basically what you'd get out of MACD. It is soft clipping that is not sine-based clipping, but it's also not got a hard edge. It's a nice little linear function. Now we undo that, and we'll get our sine back again. And let's start looking at what happens to this algorithm. This is what's in MACD as we continue fooling with it. Like, watch. I think I picked that for a reason. Like, let's go a little beyond. Now see what we've got. We picked that particular spot in MACD and all subsequent things of that nature because that is what you get when you're distorting something that's clipped to exactly 1, hard clipped coming in, and then applying that algorithm. If you stop at the figure that I've got in MACD, you get a normal clip that is a soft clip, but it doesn't start ducking back down again. As we do this, it's still a smooth function, but it is a smooth function that is doing a funny wavefolding thing. This is essentially what wavefolding is. But we'll continue. As we go farther, we're hearing an interesting effect, and that's because we're clipping even more, but it's ducking back down even more. Like our range goes from -1 to 1, and we're limiting it to that, so we can't do anything more extreme. Let's undo that and don't save that change. Check this out. Remember how I said that we could make a asymmetrical distortion? Watch this. Here's our sine basis back again. Actually, no, let's not normalize that just yet, because the point I was trying to make isn't necessarily about that, and I wonder whether I can soften the clicking between these things. Select, auto extend to zero crossing, boop, and if we're going to do this, it might as well be nice, so let's make it nice. Actually, that's not nice at all. I better continue it. Or is it? Just a moment. Yep, still got an issue with that. Oh, that's not right. How about, there we go. That's nice. Now, and maybe I can even smooth the splice at the end. There, you see what I did? That's just editing this because the click is a bit annoying. Now, remember where we were at? Remember what we did? But the thing is, this particular idea, I'm not worried about that. And remember, I don't use oversampling. So check this out. A little hard to see, but that's because we haven't got much of a change on that yet. So what we're going to need to do is amplify this all a little bit. I just saved it, so we're good. Let's take it to -1 dB. That's probably too much, so let's not. Let's take it to -2 dB. A little farther away. Hear that noise? Asymmetrical distortion. Right there. What we are doing is the one side of it is still functioning the same way that we demonstrated before. The other side is not clipping symmetrically, it's expanding. And it'll expand hard enough to do hard clipping at this edge. In fact, I can probably make it a sharp-cornered triangle by just distorting it even harder. And there we have it. So turning it up all the way means that now the top part is doing its soft clip, and if we had it turned up all the way, that would extend all the way down to the center. It would be a peak value of 1 multiplied by itself a bunch of times, subtracted by that would become -1. On the other side of the waveform, this is where the asymmetrical stuff is kicking in. This is no longer curving like the sine wave that it originally was. It's doing quite the opposite. That is steepening as it goes into full clipping. And if we were doing this in Logic or something like that, where rather than going to a DAC and playing back over speakers, and the DAC will only take between -1 and 1, if we run this in Logic, we're going to start peaking hotter and hotter on the negative side. The waveform being represented, if you remember, that what we're doing passing stuff from plugin to plugin is we're passing 32-bit floating point numbers. They are not limited to just 1 to -1. So this doesn't actually stop, this continues to a sharper and sharper point as we go from this sine wave shape. And of course, if we normalize it to literally 0, we're going to get the most striking effect of all, which I will attempt to demonstrate. Boop. And you can pretty much see it right there, that with this particular curve that we're using, set up this way, it's kind of an interesting effect, actually. This is why I think maybe making a bass plugin along these lines might be good, might be fun. We have a frequency that is adding just a third harmonic or something like that. It's like one, it's a neat little, like if we took this and it was happening on thoughts. You can, however, see with this that the way it's going in this direction, it started out as a sine, just smooth over and then smooth under. Now the over is making a very decent approximation of a sine, which I did not intend, but that's interesting to discover about. This seems to be the same, like here to here. Let me change that selection thing again. Supposing our 0 line was directly through the middle of this. Here to here and here to here look to be about the same length. So what I've got, since this is 1/2 of a full cycle, and this is going one cycle and then sort of like 2 cycles, we have something of a artificially generated literal second harmonic, only not. And the interesting thing to me about this is that we have these fairly smooth curves here. I might want to fool with this and see whether I can get it even smoother. But as it's going through this 0 point, that's pretty clean. And then as you can see, as we're going into -1, it clips here. But if we didn't have that clipping, this would be peaking out at some outlandishly, in fact, maybe we can even demonstrate that. Let's take all of this stuff away again. Not save past that point. Comment these out. Let's see what fresh hell we have wrought. We're now doing the same. That's got nothing to do with tube amps. You just might like the sound of it. I got some experiments I want to run here. Firstly, let's demonstrate the thing that I was talking about. This day might be just all demonstration and explanation without generating an actual plugin, in which case I'll generate one by next Sunday that you can have. But we're doing the exploratory thing today. Now let's normalize this and then view the behavior. Oh, hello. What are you doing over here? That looks irregular. Why does it look irregular? It's just the representation on the screen. See how it looks like these aren't peeking out at the right quantities, but then if we turn it, scroll it in, it looks just fine. Now watch what happens. And then I will do my experiment on the other thing. Peeking out at 0. See the little number? We're now peeking out at 3. Or there's 3. So the one side is being clipped and the other side is being expanded to 3 dB beyond what it already was. But wait, there's more. We can make it do literally spiking out to twice as loud as we started. The one side is being pretty smoothly clipped. And then this other side, although you can't see it, the meters showed it. When we were fooling around with this, the meters showed that the spike went down to a sharp point 3 dB beyond what we already had. And to tell you something else, I can build an effect stack such that you can see what happened. New effect stack, Bendybus, and since this is a chain, and all of these effects will be applied before you see it in the end result, it's not going to clip what I've got between plugins. We're in floating point. It's only when it gets to the converter and displaying it on the screen that we're actually clipping. So, one more effect, my word length shift gain. As you Airwindows fans know, I can't say the name of this plugin on YouTube because they think I said something else. Let's go 3 bits down and then normalize it back up later. And apply and close. And check that out. And now if I normalize it so we can see the full size, that's what we had. There's your asymmetrical distortion. On the one side, it's distorting it completely and going right down to what's basically a wavefolding, but it's only on one side of the waveform. We don't have it set up to change that in any way. On the other side, it's going to be significantly louder than the original waveform was coming in, and that's a sharp little spike. You can see how it's continuing to steepen as it goes to this point, but since it started out as a sine wave, it can't actually make that be any sharper. But a side effect, that also has something to do with the way this works. So we can continue steepening this effect by adding more and more of this power factor. See, it's multiplied by itself a kabillion times. And then lastly, times gain. It matters as to whether we have a odd or even number, but since I copied 2 and then pasted them, we're going to retain the same behavior, so this is still going to be asymmetrical. And when we build this and apply it, we'll see what it does to that waveform. when we have an even higher order power factor. When it's just, let's do our things first. We gotta normalize, zoom in nicely. And we did not save that effect stack, but it's fairly easily replicated. It's even going to remember what we had it set to. Apply and close. Check that out. Now we have a different shape. There's our new shape. See what's happening here? When we do this, what's happening is as we continue to clip, our intermediate stage is more linear until we get to the edge of the waveform. And I think that the 0.17 whatever is still accurate as far as giving me a flat wave top. But of course, when we expand it all the way up to a gain of 1, no matter what we do, you know, this is possible if we use POW, if we use the slow calculation POW. If we are limiting it to -1 to 1, we're always going to have the ultimate power factor peaking out at the center area. The sign gets turned into this. I think we're also going to have a higher and higher spike as we go until it starts to kick in and starts to pull it down. And of course, when we get to 1, it's right down to the center again. And if we had a symmetrical distortion, it would be doing exactly the same on the other side. And that gives us a funny sort of little wavefold where this edge is, this is no longer an even frequency. It's no longer quite the out of phase second harmonic that it would otherwise generate. And of course, what we see with this is that it's remaining flat for a long time, and then it starts steeply spiking to this point. If we kept doing this over and over again, let's make it go crazy. I'll tell you what I'm going to do. Do I have this? No, I don't have anything up there. I'm looking for my little for next. I'm so busy thinking about this that I don't remember how to do a for next loop, but I've got it in code somewhere. So let's go find something that has it. This would be something that has it. One of the Z notches. I have a for next loop sitting around up here defining this stuff. Input symbol. let's see what we get. So this for loop applies only to the single command right after it. If I put it in brackets, then I'd be able to do more, like this is brackets, and that would allow me to do multiple things in here, although I don't actually have to because it's still only one statement. But with this, there's only one statement, there are no brackets, so this loop is only going to do this many times. And this should be the same as what we had before, and let's find out. And we're not even going to attempt to scale it because we're experimenting with other things now. Back to our bases, normalize it. Never did save that effect stack. Fine, time to do it now, I guess. And there we go. There's our effect stack. And see what we've got? We have got, let's see. We got something. I wanted to replicate what I had before, so let's fool with it. Instead of ×4, we'll call it ×5. And we're trying to generate the same thing that we had from before. Putting into this variable factor this many times, and I'm basically trying to reproduce what was there originally. Honestly, I think I might be in with the chance, because I remember I did have to normalize it to see it properly. So let's roll all that again. Finishing up my chai tea. Firstly, we're going to make our sine wave go exactly from -1 to 1. Then we're going to fire this off. And you know what? I think there is another thing available. Unless there isn't. Nah, it's not letting me do stuff on the DAW level. It's only letting me do stuff on the plugins level. And I do not have a normalize on the plugin level because I'd have to scan over the entire thing, so never mind. Apply and close. Then we'll normalize. And see, we got that again. That's what we had before. So now we know that we've just reproduced this. So now what we do is go crazy bonkers. Hundreds and hundreds of power factor. This is going to grind a bit, but I don't mind. We're actually processing offline. Watch what happens. Because that's much easier than copying and pasting input sample that many times. And we will now see what we get out of this same algorithm pushed to the nth degree, or the 900th degree. Normalize. effect stack, and normalize again because we're limited to 1 and -1. Check this out. Isn't that interesting? We could be doing the same thing with symmetrical processing, in which case the frequency that you had would be making this spike go the opposite direction. And by the way, this sounds like this. And it's not necessarily that smooth of a thing to listen to, but we have now generated a artifact on our frequency which does actually scale by the size of the waveform. We've got it so that it only kicks in at the very, very tippy edge of the waveform. If it wasn't literally a sine wave normalized to 1, it would never actually reach this point at all. This is like a bizarre clip that kicks in. Which also means we could simulate the dangerous behavior of the TL071 chip, where if you drive it past its power supply rails, it flips over to the opposite side of the power supply. And that is some bad mojo. Now, let's fool around with all of this even a little bit more. Here's our parameters and numbers and things. Now, what I'm thinking about here is there's something further to do. And you might be able to guess what it is. I think that'll work, because I think this is our modulus operator, but I could be mistaken, but we'll find out by trying it. And I think it's going to go between 0 and 1, but I could be wrong. Remember how we do the absolute value thing? No, we're doing this, and then for every other power factor that we settle on, it'll do an additional multiply, but by Fab's input sample, meaning that if I chose this correctly, everything is going to be asymmetrical. If I chose this incorrectly, everything's going to be symmetrical, assuming that this is the modulus factor. And power factor mod 2 will tell me whether it's odd or even numbers. But what's going to happen now is I will have a sine wave where I can do a kind of weird frequency sweep on it. Well, let's find out what that's like, and also what it runs like as a live plugin rather than post-processing. Oh, L value required. Where we got here? Oh. Here's what went wrong. You see what I did wrong? This is the dumbest programmer problem ever. Check this out. Power factor modulus 2 is decreed to be 6. Oh, but wait, you can't actually assign a value to an arithmetic thing. We're not doing a logic check. We're not asking this as a question. We're telling this now. We'll put it back to 0 because that's the question I meant to ask. And we'll put another equal because this is a logic question. Is this equal to 0? Rather than being a assignment operator of please make this mathematical formula be a number, because the mathematical formula is not a number. That's a dumb, silly mistake, but that's why it's at L value. And this part's going to be fine. That will have fixed it, and sure enough. And now let's hear what we made. And when I say hear, I mean we're going to actually hear it because I am going to normalize and then run the plugin all on its own. Although, no, come to think of it, no, let's not. Let's run the effect stack and see whether I chose rightly. We'll pick some large number, assign it, and undo it and pick another random large. Actually, no, we don't even need to do that. So what I've got here is a thing where all of the settings of this control are going to be asymmetrical. But I think that it's actually better to have it be symmetrical for this. And that's going to give me that. If the modulus factor tells me it's an odd number, now we switch it from asymmetrical to symmetrical, or vice versa. That'll build fine too. And we're going to normalize, and then let's run that same effect stack again, and this time it's going to be symmetrical. So let's start playing with this, and it seemed to take a long time. I think we might just have an effect that will crash and die, but not if we have very small values. So let's listen to it a little bit. Oh, we're loud, aren't we? We are not actually being able to do that. Maybe what's happening, check this out. I think maybe this modulus thing is not actually ever giving me a 0. Maybe it's only giving me 1s and 2s. Let's try what we get when we set it as 2. Because I can tell you immediately what's going wrong. That's telling me that that calculation is not working. So I've just changed that number to be 2 instead. I thought what I had was a thing where it was always going to give me asymmetrical, but what I really had was a thing where that's what I was looking at. And now let's fire up the test bed. Yeah, here's a problem. I don't know exactly what's going wrong here, but it's going wrong. So what we're getting is alternately Oh, I bet I get it. See what I did there? Now let's see if it worked. If it did work, I'll try to explain what I did. If it doesn't work, it's a moot point. The thing that I'm observing is this bouncing back and forth between 0 dB and 6 dB peak, which tells me that it's bouncing back and forth between asymmetrical and symmetrical, and that's what I'm trying to avoid. See, that is asymmetrical. So this is what we're trying to do. And since that didn't help, I'm not concerned for it. And let's take it back out again. Every time we multiply by input sample, we might be flipping the polarity. I'm trying to calculate based on power factor here. See, I wonder whether this modulus factor is screwing me up. Well, for starters, let's find out whether the modulus factor thing even engages at all. And I'll tell you why or how. Now, if this is true, this is automatically input sample, meaning that the end result will be silence. Let's find out whether this stuff even engages at all. This should be cutting in and out every other value of power factor. I'm trying to do it on odd numbers, or alternately even numbers if that's what I need. Okay, well then let's change that again too. We'll ask whether it is mod 0 and rebuild. And then we shouldn't even need to normalize. We'll hear this immediately anyhow. Is this cutting out? Yes. So on odd numbers, it does cut this out. Therefore, this should do something. Maybe it's a combination of things. I had tried that last thing with power factor mod 2 equals 2, which can never happen. So let's find out whether going back and doing it again. If this works right, what's going to happen is it's not going to bounce between asymmetrical and symmetrical. And that could have usefulness in a variety of things I might be able to build. If this doesn't work, it'll continue to bounce between asymmetrical and symmetrical. And if it does work, I actually don't know which it will end up being, so let's find out. Okay, it worked. This is strictly asymmetrical processing. I wanted to do symmetrical instead, but the overall calculation was what I was after. Quick little change. Boop. Having made that change, now we have a thing that will always give me symmetrical output. That's the mod that I needed to add. What was going on was I was having the odd and even ones consistently generated, but all that was happening was if I found that it was odd or even, it would do the fabs thing, but then it would jump ahead a step. It's hard to explain. Anyways, this should work. And we can also see whether it blows up my little laptop. Thankfully, Apple devices don't fry themselves to the point of not working anymore. What's going to happen is if I demand too much of this, then it's just not going to process right. It might crash the program. It's not necessarily going to, unlike the A10 Mini, I can ask the laptop to do too much and it won't die. It'll just not feed audio properly. All right, let's roll. And 0 means we got nothing. And our first stage is kind of quiet. And it's able to run full crank. That's interesting. I don't have a CPU me to run this, but this is going to be grinding pretty hard. Hear that? Sort of a weird new form of filter that only applies to sine waves. Let's take a moment and look at the very smallest one. If we apply this, what we get is symmetrical, and looks like that. That's the gentlest form of this processing, which is your sine wave, and then it's subtracted by basically itself again. And if we tell that to be a hard clip by having the threshold be set to the correct amount, that will still be a flat top, I believe. But it'll be well, we can find out, can't we? Don't save. And one further thing. Zero is going to be 1, so the slider will only go down to the most limited factor. Because I know if power factor is a literal 0, then this never happens, and input sample is just minus input sample, so it winds up being silence. But remember what we did in the very end of all this? We've broken what's in MACD down into these tiny little functions. And now we can apply gain to do the sort of flat topping thing that we were talking about. And I'm trying to decide whether to put a limit in here as well, but it's probably no point. Oh, can't do that. There we go. And now we've got our, well, we got to normalize it first of all. Make sure that we have the most extreme possible results to have. Then gain of 1. Oh, wait, hang on. Something's wrong. And I keep forgetting to close this window before doing this. Oh, I made big problems here. There's a variable, and then I'm trying to do it again. So this is all messed up. Let's not have it be all messed up. What should we call this? Can't use the same name of a variable for two separate things. That doesn't work well. We'll call it iterations. We're not using that word for anything. And that goes here. We can actually put that up here too if we want, like because we really don't need to be recalculating that every sample. It's already leading to enough mess and difficult processing, so we don't need to recalculate that. That can only change when this changes. So we're reading this outside of the sample loop and inside of the control update loop. And then generating this, and this is acceptable within here. Forgot to normalize. Yeah, where my head's at the moment is figuring out whether I can do a quick little thing that I can put out on Sunday that you could throw in a bass track on something that was very mellow and bassy with a consistent volume that would function as a neat little sort of frequency doubler. Because I was getting an interesting sound out of some of that stuff. Now, what do we got? And there is this, and here is that. And of course, as you remember, this is a cool effect, all right, but, and if we apply it, it looks like this. That's what that sounded like. But that's with gain of 1. If we have it down at the relatively small number of multiplications and dial this, to, I think it was like 176 or so. I would have arrived at this experimentally. And then we crank this up. What do we got? We wind up with a little indentation. We're limiting the amount of maximum effect this can have, but it's also a factor of how many multiplications we have in the power factor. Like, there is going to be a stage here where I can probably find it experimentally too. But this is not a sawtooth, not even close. This is a smooth little divergence that's being built out of the sine wave. It's essentially, every piece of a sine wave is still a sine wave no matter how much you multiply it. So this flat spot on the top, if you turned it up enough, it would end up being its own little sine wave. And that's essentially what we're doing. So when we have this, there's going to be a place where it gets louder and louder. And that's because we've gone beyond the maximum distortion factor. So I got 1.68 here, and our gain is set to what would be a flat top. And then there's a point, that's 1.64. Let's see how much of a flat top we have here. And sure enough, we are now exploring spaces where, with this enormous number of multiplications, we're making it steeper. We're making the clipping more sharp-cornered than McAtee. This is the gain factor relevant to McAtee. As we continue to steepen it, it stops being a flat top and starts being a waveform that goes all the way up to pretty much 1.0 again, because we're steepening it, and then the flat top goes down to exactly here. So that's the way this is all sort of tuned. And that's interesting. I could probably calculate it out. Want to give that a try? This is for anybody who wants to program plugins yourself. This is the kind of stuff that you'll be doing if you're trying to do this. I just said, want to give it a try? Let's come up with a way to make it so that this always flat tops, no matter how narrow the space in there is. That means I'm going to come up with an algorithm where, however steep or flat, I'm probably going to cut down the maximum range here so that it's more controllable. I will make it so that the sign going from 1 to -1, no matter where you put it on that calculation, it's not going to do this ducking back in again. It's not going to do the wave folding. So let's see whether we can find that number. I have some shrewd guesses. Here's my first guess. And I'm going to promote the int to double precision so that I can do this calculation. This might actually be a float. I don't care. If the one thing has been promoted to double precision, then I think it's going to have to do the entire calculation that way. So let's see what we get. This has just limited the amount that this can affect anything to the sort of maximum size of the calculation. But this is, oh, I wanted to do something else too. Let's do a maximum calculation of only 10. That is, in fact, an unused variable. You are quite correct, compiler. Now let's see what we got. This should be interesting. Could be true, could be not. Normalize to 0 dB to get me my exactly 1.0 maximum amount. Fire at Bendybus, and let's hear what we hear from doing this. This is what we kind of expected. Let's see what it looks like here. Oh, yeah, that's not right. Let's see what it looks like at some other places. I have maybe an idea as to something that might fix that. See, same problem in that we are continuing to have that not flat-topped wave. Whereas if I do this exactly right, it'll be perfectly flat-topped. So that was clearly not correct. Let's see if it is consistent across everything. It's starting to look more flat-topped, but that only means that the amount of difference we have in there is diminishing as we go. Therefore, (1.0) divided by, let's say we're off by 1. If we're off by 1, I just fixed it. Therefore, let's find out. Do our normalize. Fire up our plugin. Sounds kind of smoother. Here's our maximum. What do we got? And ladies and gentlemen, that's the answer to that question. We can probably also do another interesting trick that I am... So that's going to be about 6 dB down, right? We might have something amusing here. I think it was Bro that was asking for, give me a tube. Well, watch this. And we might want our hard limits here for this particular magical trick. Not that it's going to affect anything right now, but for future reference. Notice how it started cutting down the gain? Notice how factor is this. we're going to do an amusing little trick. Steal this, put it up here. That is now the same as what we had before, but we have this number now, and we don't need to keep recalculating it every time. Hush you. Now, gain scaling 1.0 divided by power factor plus 1. So that's going to be, factor is being scaled by that. Yeah, but I needed to do it again. Remember how I was trying to get that flat top for the waveform? But this has just told us something interesting. So if it did not do power factor plus 1, it needs to be so that when it's at the smallest level, it is, see, when it was just 1.0 divided by power factor, if that was 1, it would be 1 divided by 1, which equals 1, and factor would be times equal 1, and therefore at the lowest scale, we did not get a flat top on the most attenuated wave. Thing is, now that we do have the flat top on the most attenuated wave, it is time to figure out how to scale the output back up again by a parameter that makes sense here. And that's going to happen after we apply this. And it's going to be input sample times equals something. Now that means we've got our gain scaling. This is going to be 1.0 divided by 2 for I got a hunch. Here, let's try something. Here's another 1.0 plus something, but this time it's because we're trying to amplify, but if we amplify by big numbers, it's definitely wrong. But if we have, remember multiplying by 2 is like 6 dB. We don't necessarily want as much of that, but we might want as much or close to that. Let's just see. Let's just see what we get. That's what I had, right? Yep. So we are now multiplying, we're boosting the gain by whatever we had here. And that is, if gain scaling was so tiny because power factor was enormous, it's virtually nothing. But if gain scaling is smaller, well, let's find out what we got. Oh no, that ain't what I want. Oh, behave yourself, silly computer. Remove from sidebar, you were never intended to be there. All right, back we go. Normalize. So if we have a very high gain scaling here, and this no longer does anything, we're not clipping. As we dial it back, it's going to start amplifying it the smaller we get. To the point where this is now our flat-topped and softest possible wave. And that's a distinct change from an actual sine. That's way flatter topper than the sine is. Even though we're not doing a sine calculation, we're working with a sine to produce the softest possible soft clipping. But we're not amplifying it back up to 1 again, and that was the idea, so we're going to fool with this a little bit more. 1.0 times, we keep going up and down by things. (1.0 plus double gain scaling, because gain scaling did go back to, well, never mind. Too many words. You saw what I just did. Let's see whether it did any good. Because this is a number that's going to get larger and larger as that slider goes closer and closer to 0. And I got it set up in such a way where 0 is the fattest, biggest, softest clip. Now let's see what we made. (0.84 or 0.58). Exactly 0. That has just given us our soft clip that peaks out at exactly 1. Only thing, there's one concern here. It's peaking over 0 sometimes. See? And that's not what I'm after. So we have a discontinuity here. And we've got it where I can bring it right back up, but we have a problem in this calculation. Probably means that rather than doing it this way, we want to do it some other way. So gain scaling, we had this and it wasn't exactly right. Let's find out what happens when we instead simplify this. And gain scaling is power factor plus 1, but output scaling is 1 plus without power factor plus 1. That's just an intuitive jump. Could be completely opposite from what I want to see happen, but it also could be in the same ballpark. I'm just trying to bear in mind like the variations and how these can affect each other. And I will know if it comes out right. If it doesn't come out right, I guess I won't know. Nailed it. So we'll talk a little bit about what just happened. But what we've got now is our calculation that does a flat top on the top of the waveform. It's peaking to exactly 0 perfectly. And this is the only control that we have. If we apply it, we can see that it is making a flat top of an incredibly tiny space. And it makes basically no difference to the sine wave. The sine wave is still very much a sine wave here, but it's a hard clip. Whereas, we scale that back and then we start doing it differently, as in tiny area, much larger area. So it's soft. It's a small boost to a larger boost. Now, that is a massive soft clip, complete with the gain boost that it requires to be implemented. And I'm going to take a second to explore what that feels like in the very small amounts. Like I hear that kicking in here. But this, no, that still looks like it's being flat topped a lot. It's the ones way over in the end that aren't, so let me delete that without saving. One to 10 doesn't seem to be very relevant here. Let's do 4. We'll do 1 to 5 and see what that seems like. But one more thing. Here's our sine bases. Oh, normalize. Very little. Too fatter. And welcome to Alien Kittens. Not much of a difference with the bypass. I don't know though, I hear it. I'll let that bass kick in first. Bro, there's your tube effect right there. We have made it. We has made it through to the other side. Let me pick something else. Maybe a bit of Rain Dragons. Bypass. Exactly. That's exactly the point. Tube effect increase. Diminish. Increase. We have a really transparent form of extreme soft clipping that does not use a sine calculation. And the higher settings of this tube effect actually run less CPU. Double entendre, are you joking? No. Explain to me what a multiband split has to do with tubes ever. I've built tubes. You know, your proper power supply stuff and everything. It's your big old soft clip. Alrighty. So I think we can have slightly more of this. We'll call it 5 plus 1, maybe even more. I don't understand what you mean by black box thing. I don't understand what you mean by multiband processing. You're losing me. You're losing me. That is super duper unhelpful as far as getting an actual tube sound. I'm going to need better explanation than that. Multiband processing has nothing to do with making stuff sound like tubes. This is actually a pretty good job of getting there. The sort of faint loudness boost. At any rate, we do have this going on, and that's nice. It is a tight little cluster of stuff. We can make it an even tighter little cluster of stuff if we want, like this. I've scrolled down as far as I can, don't know how to help you there. And I think I kind of like the idea of having okay, parallel/multiband processing has nothing to do with making stuff sound like tubes. So making it sound like a particular other VST, yeah, you guys lost me there. That's not where I'm at with this stuff. That said, let me take a moment, because I'm getting to the end of my stream. I think I have something that I can give people on Sunday. Might be kind of dumb music tricks, but all the same, I think there's something that I can give. That said, you keep talking about multiband. Well, you're not the only one. And people have asked me for things like that, and I've never actually done this one before. See that? Might be possible for me to put this out. Somebody's been bugging me for this kind of thing, and it's never been released as a VST plugin before. what the hell this does. This is from a long time ago. So if this is the sort of thing you're after, like we've got stabilize, it does this. Unstabilize is that. Matrix is kind of like gain level, but it's really not. So yeah, as far as that kind of stuff goes, there is a multiband thing I could give you. It's this. It's from a long time ago. I don't know what it does, but I think I could probably do a VST version of it, even though that's very mysterious. And I don't remember how it works. If indeed it does work, if you want to call this working. Yeah, apparently you can do this. Stabilize of 0, we got this. 1, we got that. Halfway. I don't even know what this is anymore. So yeah, clearly we need to let people have their hands on this. This is my take on... Oh, good Lord, don't tell me the image is cutting out again. We do not need the new ATEM Mini to be frying itself also. And yet that is what is happening. Well, if it just continues to do this, I'll have to return it and get another. I see that happening. That is indeed happening. What happens if I take away this? All right, so multiband distortion is a terrible mistake that you should not have. But there you have it. It's a thing, kind of. I wonder whether maybe some of the bizarre... I could test this out by trying to plug this laptop thingy into a actual HDMI monitor. Yeah, I seem to have just fixed the black screen flickering, and the ATEM is running hot, but I wouldn't call that crazy hot, and I should be able to control that even more. But maybe some of that has to do with just this particular adapter flaking out. That said, we got back. We do not have the flickering anymore. That's scary. I don't want this ATEM to die. It would be a drag if I had to permanently stop doing coding streams on the back of that. That would be a drag. And off it goes again. Doesn't like something about all this. Positioning on the screen, maybe? Amount of black pixels on the screen, maybe? Anywho. What we have here close to done, but maybe not quite. Param 1. I should touch that cape up. Interesting. So this HDMI converter, from God knows what this is, that is going from the laptop to the ATEM Mini is itself heating up like a bomb. Interesting. So it's not only a matter of the ATEM heating up and flaking out, the actual HDMI converter cable may also be heating up and flaking out, which means there's a separate fix for that, which is put a heatsink on the plug of the cable. Go figure. For now, let's build this one more time, because I'm about done with my work for the day. It's not going to be called Bendybus. Oh, wait. I have an idea. Just because this is like a dumb tube tricks thing, I have an idea. Gain equals 1.0 plus param 1 and 1.0 minus param 1 and all of the different things that one can have. And it's going to be input gain, so okay, so pretend this is named something else. But firstly, where is our assigned basis? There it is. We'll normalize this, and then there's a sign. And now we're pushing the sign to be super loud. So loud that it's clearly flat topped all to hell. It's practically a square wave now. And secondly, you mentioned earlier that alien kittens might seem a little bit like louder when you turn this thing up. We've just enhanced that a little bit. Alien Kittens is already so bassy and loud that it's just about clipping, so you can't normally push it any farther without a lot of nastiness, but bypass. So we now have a tube style loudinator. Here, let me back this off of here. Cut it in for just a little hint of loudinating. Progressively boostier. To just silly. And if we do the same thing to, I don't know, drums maybe? Here's a drum track. Come on, you. As we turn it up, never peaking past 0, never having any crunchy loud clippiness. Quiet, much louder. And lastly, what else do we have to demonstrate? How about this one? Sort of also very bassy, because that's something where you're going to want your tubey style loudinator silly person trick to be fully on par. So to what extent does this make this already fat sounding track sound even more insane? Let's find out. So that's pretty big. This was bass bypass, so even with it on 0, you're still getting something. Progressively fuller. Bypass, engage. I think that'll do. I think that'll do it. It's not precisely what I had planned to do today, but all things considered, it's nice to give folks like fun stuff, and some of the experiments I meant to do today I did in fact do. So we're going to call that a day, and I am happy. Actually, there's several thoughts here. I'm touching the cables in the back of this device because this is, of course, my thing. I've heard it said that you're supposed to have cables in this device when you're running it because they're part of the cooling system. If that's the case, then that might be giving problems to the adapter cable from the laptop and vice versa. Like it would cause the laptop converter cable to freak out, and then the laptop converter cable itself doing some processing and generating stuff would also be making it harder for the A10 Mini. So I might be thinking in terms of some kind of little extension cable I can throw in there, seeing as, you know, it is possible. I bet I can do that. I'm not sure how soon I can do it, but I bet I can do that, and I bet I can, it'll be of some help. Because it's very much a thing, controlling the heat from this device and keeping it from frying itself. But it didn't really strike me that I could be having problems from both the ATEM and the laptop cable. That's just too much of a good thing, too many problems to have. But we'll try to solve them regardless. And you will have this crazy, and bear in mind, this is not going to be the most controllable thing in the world. I see this as kind of like, what's that one that was out there? It's some kind of demented multiband thing, and it was like Sound Goodizer. This is like that, but Airwindows style, in that it is a soft clipper with a really lush tubey sound and the ability to take a knob and just push it for more. Because even with the with no input gain boost, it still does the increasing fatness thing. It's worth thinking about. We'll have to see whether some kind of more sane input trim makes sense. Because the deal is, I can have it with just the regular behavior. And the last thing that I added was a input gain boost. Oh, Joku Sekovan, apparently with the ATEM Mini having HDMI cables plugged into it composed as part of the cooling system. This is extremely dumb, but I wouldn't put it past him. Blackmagic make really weird choices around cooling their stuff, and that's why I'm going to go to a lot of trouble to see to it that this current one that I've got is controlled well enough that it doesn't melt itself. But I have heard that. It's just not a sane thing to do. But it could be possible. That it could be true that that's the way it's meant to work. So yeah, that's my final thought. I guess if anybody wants to sound off on that before I log off, that's fine. But the final thought is the last change that I made to this plugin took it from being a one knobber to a dumb plugin tricks one knobber, where it has a built-in 6 dB boost on that control, on top of the roughly 1.5 dB boost that you'd already get. So it just sort of kicks in harder and harder until it goes to a very silly stage. I'll fool with it and I'll see. I'll run it on some of my test audio. I have test audio that I don't like to use on streams because it's a company that did a really long compilation of copyrighted music that you're supposed to use to compare stuff with. I'm pretty sure I have it there, but I might have hidden it away because I can't really be playing it on streams, but I can check on it on my own. And I'll decide how much gain I think is appropriate to add for this loudinator thing, where as you turn it up, what you end up getting is, at max, is the softest of soft clippings, exactly scaled to exactly flat topping the wave, which is part of what happened today, and then scaled back up again to full crank. That's the thing, is I could put pre-gain boost in there just to sort of further make the point, but I don't have to. And I think it'll depend upon how it sounds and behaves in various test signals. I'll get something. And with this one, I'm not really worried about doing the correct thing. I'm going to do the cool thing and make a plugin that people will have a lot of fun with and will enjoy. Oh, the album that you were hearing, one of the albums that you were hearing was Dragons. One of the songs you were hearing was a thing called Twilight Sparkle's Eyes. Yep, not joking. And yes, HDMI cables as cooling is extremely dumb. So on that note, I will talk to you folks later. I'm going to go and have a bit of a lay down. This was good, but also a wearying stream. Talk to y'all later. Bye-bye.